All right, we are started. Hello,
Yeah,
everybody. Hello, Ben. How are you?
I'm a little tiny bit under the weather, but okay, pretty good, mostly. Just
Yeah, I
feel
usually sit here like a lump until it's time to start, then I liven up, right? So
yeah,
it's like I get the adrenaline going here.
that's cool. It's good to see you, man. Um,
Yeah, good seeing you. We were just talking about Windows. Windows just tried to make me reboot my machine right as we're setting up for this show. Darkened everything on my screen. Windows decided that what I was looking at wasn't as important as what they wanted to show me. And so, right in the center of my screen, they put a thing that said, reboot now. And they gave me other choices. Oh, do you want to reboot tomorrow? No, I don't want any of the three choices, but I had to pick like tomorrow. So it's their way of putting their foot on my neck to tell me, well, you have to reboot soon. You've said no too many times.
yeah. So I was just lamenting hearing that this sort of thing has happened to me recently a number of times that and it's always at exactly the wrong time.
Yeah,
Like I don't
yeah.
I don't ever recall ever being notified of an update for an operating system or some other software as I'm just about to get ready for bed. It's like,
Right,
hey,
right.
can't they look at my local clock and sort of surely they're gathering statistics and data on the machine, even anonymously, but about me and my habits of using the computer. Surely they could wait till they know I'm less likely to be disturbed by this. But no. And the
They
same thing with
supposedly
phones,
they
right? They used to update. AT&T used to push out updates to my Android regularly. That each time the software got updated, I would say no, not now, not now, not now, not now, not now, and eventually it would just do it without asking. And
right.
and every time the battery life got worse. And then
Gee, I wonder why.
and then and then I think it's probably 2 years ago now. There was finally someone took them to court in a class action, and they stopped deliberately using software to kill
They
phone battery life.
said they stopped. They
Well,
probably
I
have lots of unverifiable tricks that
that's
they
true,
still
and
do.
who knows for sure, but I do note that since then I have not had that specific problem. So
Right.
I just think, these big companies, they've got to be someone somehow has to hold their feet to the fire. Just like we also the government is a company that provides services for citizens and also needs its feet held to the fire for things. But
Right, right.
uh,
Well, it's like right to fix, you know.
oh
Uh,
yeah,
I
oh my
I
God,
don't know where we're at with that. I think there were some victories, but I think there were some setbacks. If anybody knows where we're at with right to fix, but I'm a firm believer. If you buy hardware, it's your hardware,
exactly.
and I have this problem with Cisco right now. When you buy Cisco routers, you have to pay a subscription to enable the 10 gig interface. Well, wait a minute. I own the 10 gig interface. It's one thing to do a subscription for the iOS. All right, we've lost that battle. It's subscription. But you want to enable my hardware, I have to give you even more money to enable hardware I already own. Don't tell me it's the cost to develop it. I already own it.
Yeah,
It was cheap enough you sold it to me.
yeah,
So, yeah.
yeah. That's a gray area that needs to be made more like a thin black line to me too, because it's like I'm an electronics designer, you're an electronics designer. We have these capabilities in our CAD tools called variants, and they're there
Right.
for that reason. There's absolutely no problem designing a circuit board to suit multiple products, and then you do assembly variants to give you those different products to sell at different price points based on what your customers need and what the market demand is. And there's always market demand for a cheaper, simpler version of something versus a full-featured,
Yeah.
more
Yeah.
expensive. Software configuration and licensing is the same, and I have no problem with that. But it's kind of weird when you have a software configuration that's turning on or off hardware. I feel like that's fraudulent,
Yeah.
and it shouldn't
Yeah.
be allowed.
Well, the other
And if you're a company and you do that, you can look forward to people finding workarounds and hacks that override what you've done and unlock those features anyway. Just like the Regal, when they launched the DS1052E, and it was a firmware change that turned it into an 1152E. Now, they may have actually leaked that deliberately as a marketing stunt, and if they did, my hat is off to them. That was utterly brilliant. I hope that was deliberate. Talking about instruments, I've got a new one.
Okay.
Finally got a KV901.
And what is a KV901?
KC901V, sorry. This is a basically, is it DC? No, it's 9 kilohertz to 6.8 gigahertz VNA.
Oh, cool. So you got
Handheld.
yourself a 6 gig VNA.
Powered by lithium batteries on the inside with a charge port. It's got, I haven't figured out yet how to best use the Ethernet, but it's got Ethernet, memory card, USB. So, for all your screen captures. It's just a 2-port. I can't show it to you in operation today because it uses N-type connectors, which is very common in the higher end test equipment.
Right.
Everything I've done up to this point, RF, I've done using SMAs or PL239s, ham radio, antenna type connectors and coax. So I
keep these laying around for that reason, N-type to SMA connectors.
I ordered some of those, but I'm still waiting for them to arrive. So perhaps next week or the week after, we'll get into fiddling around with this.
At least they're not part of the part shortage going on. They are available.
Things like that.
I lose these. My problem is I don't know where to put them.
You don't want to lose them. They're expensive.
Yeah.
I was looking at calibration kits for this. It's been calibrated in the factory, and I can use it as is. But ideally, with a VNA, you want some reference calibration loads, shorts, and opens, and you connect them, and it's like when you have a scale, a digital scale. You let it settle on the flat surface that you're going to use it on, the bench or whatever, and you press tare button, T-A-R-E.
Right.
I don't even know what that word technically means or what the etymology of it is, but you tear the scale and that it re-zeros it in the current environment. And that's why you need, with a VNA or any other RF test equipment that measures signals, you need your basic cables that you're going to be using, and you need your reference load, your reference open, and your reference short circuit to tear.
I got one here.
Yeah. You do that to tear.
It's got an open, short, through, and load, and this came with my Tech Data VNA.
Right, but so here's the thing.
And it's expensive, as you said.
A kit of reference loads attenuate, a kit containing a reference 50 ohm, a reference short, a reference open, and a reference through port costs as much as this whole instrument to buy new.
Right.
And so I'm now I have this cool instrument. Now I'm on the hunt for maybe a used set of references or something, or I'll buy decent quality connectors from Pasternak or somewhere and make them.
Right. Pasternak is love the catalog, hate the prices.
Oh yeah, but that's high quality stuff, right? So
it's high quality stuff.
Or I use the adapters and the SMA cables and the reference open, short, and load that came with the mini VNA Tiny that I have, which is it's a much cheaper instrument, but it does the trick. So
Yeah,
So
Mike Fikes just went through that. He got a VNA, and now he's trying to get the referencing stuff for it to make it even more usable.
Yep. So I know
hey, I have something to show you.
Okay.
We talked about these a couple weeks ago, and lo and behold, my son opened a drawer, and there is my 40-year-old template that I used to draw the C-128 its first time on graph paper.
Wow.
The conversation had been, well, how did you draw things? And it's hard to see here, but this little tiny AND gate, this is my favorite size for drawing. And this happens to work well on a 0.1 inch grid paper. I have a slightly larger one, but typically these were for special components or inserts. This was the size I loved, and this is the exact one that I've had for 40 years. So
this was CAD. This was herd CAD.
This is my CAD. Yeah.
It was really TAD, template-aided design, not computer-aided design.
This is made by Barrel Rapid Design. Obviously, there was no such thing as websites on here back then. Oh, it's got its logic symbols: mil standard 806 half size, ANSI Y32.14. So it's got all this writing on here that says it's a legitimate template. That's pretty funny. And this is a 3/4 size.
Yeah, that is cool stuff. That's how it was done. I had standardized templates just like it, made of the same sort of transparent green. I'd never got one for schematic symbols because by the time I would just draw them by hand, you know, with a ruler and pencil when I was in high school and younger. By the time I was 13, don't tell any of my friends at Cadence this. Actually, when I was 12, my dad brought home an IBM PC clone. It was a AT clone, a 286, 16 bit.
Right.
It had 640K of memory. It had a VGA card, and he had no clue what to do with it. I don't know what he was thinking. It was $2,500. I'm talking 1987. $2,500. He'd had a hand-me-down Apple II that he'd tried to use for some spreadsheets and accounting stuff, and he just couldn't figure it out and didn't like it. So someone somehow talked him into spending $2,500, which is a lot of money in Australia.
That's like $6,000 these days. Yeah.
Yeah. I don't know what he was thinking. I don't know what my mum thought of it. I don't know. Like, I'm sure it wasn't something they discussed. He just turned up one day with this. It was made by Philips. And it was actually a pretty good machine for the time. And I was glued to it. I couldn't stop. Like, every day I was booting that thing up and learning how to do DOS batch scripts, reading the manual.
Right.
I made my own menu system in the end using batch files.
So did I. Yeah, I had a home menu and stuff. Yeah, because I used to argue that DOS was just a collection of executables, file-based executables, except for a few things like the directory command were built in and stuff.
Yeah, and some built-in TSR capabilities with and interrupts that could be used by different programs. So I was learning all of that, and at the same time finding all sorts of different programs from friends. So I had another friend at school who was also a computer nerd like me, and David Millington. David, if you ever see this, hi, I hope you're doing well. haven't seen him since junior high school. He was a fun kid. His dad had an IBM PC, the 8-bit, the 8088 version, that was from a year earlier, or two or 3 years earlier, and he had all this other software that ran on it, including Norton Utilities. And he's like, "Oh, you've got to look at this Norton Utilities." So this is when Peter Norton was still the owner of Norton Utilities. It was good software before it got bought by, I don't know, whoever else, Symantec. So And I discovered this thing called a hex editor, and I could open any program, any executable, and look at the actual hex that made up the file that was on the disk. And I found, okay, so there's that. Then I was at a family friend's party at a house in a rich neighborhood near where I lived called Wahroonga. I grew up in a place called Hornsby. There's a rich neighborhood in Sydney called Wahroonga where all the houses are old money mansions, you know. And we were at some person's house there for some party, and apparently the owner of the house was an electrical engineer who designed electronic products. And there was a computer in that house, and the guy who eventually became my brother-in-law, who was the connection to this family whose house we were in, said, "Oh, you'll want to see this." He brought me to the computer that the owner of the house had in his study. It was another PCAT, and he loaded up, and he ran draft, enter, and OrCAD comes up on the screen, and he's like, "This is a schematic drawing program."
OrCAD on the PC. I used OrCAD. Yeah.
And
green. It was green and white when I used it. Or green and black.
Yeah, it was like version 1.6 or something. And he sent me home with a copy of it on 3.5-inch floppies. And and I could not. I spent 3 weeks, probably
3.5-inch or 5 1/4.
3.5. So I spent probably 3 weeks every afternoon after school fighting with the computer to try to work out how to get OrCAD to start, because it would load up and go to a black screen, and then it would. Well,
did you need a dongle?
No.
OrCAD originally needed a parallel port dongle on it in the old days.
This one didn't. I don't know why. It must have been an even older version.
Right. Originally, they didn't need, and then they went to a dongle-based version. And what we did at Commodore, we actually X-rayed one of the dongles, and somebody reverse engineered it, and it was basically a shift register and exclusive OR gate. So it's basically doing,
pseudo-random sequence,
folded number, yeah. It's exactly like CRC.
Well, the version I had must have been older that it didn't need that. So, and I'm the reason why they invented dongles then, because they realized lots of people were copying. Hey, but I was a high school kid just learning electronics. I was 12 years old. This was awesome.
It's not like you were stealing the market from them.
I didn't even have a mouse. Now, the computer I had a, I think it was an Expert Color or one of those old brands, VGA card, and I eventually realized, oh, this software is trying to load a video card. It needs a driver for the graphics card. So it had all these specific DRV files on the disk.
Oh, that's right. You had
I had to guess by name which each of them were, and there were all these different brands of video cards. They had a Hercules that was
right.
But higher resolution. They had, all these different brands. I forget the brand names. And then they didn't have mine. So I was really bummed, because I knew that the video card that was in the computer was capable of 800 by 600, which was absolutely cutting edge at that time.
Yep.
800 by 600 resolution that was like today would be equivalent of an 8K, right? So, but then, so they didn't have that, but they had generic EGA, and I tried that, and it worked. So I got 320 by 200 and 4 colors, and I'm like, cool, I can draw schematics on computer. And I started drawing schematics, and I found out how it had the grid, and back then you didn't need a mouse. You could just go grid point by grid point with the arrow keys on the keyboard.
Right.
That's how I did everything. Well, then I had to work out how to drive the program. I had no manual, and it had no graphical menu structure. This is DOS software, people. So I discovered once it loaded, I could see a border on, or at least the top and left side border on the screen, knowing that some sort of workspace is open here and the rest is just blank. and then I hit enter, and a menu appeared, and it had file, you know, load, save, but it had file, had, you know, hard copy, which is obviously print out, had, you know, all these different things. I forget what they are. And it had library. And I'm like, oh, library, I bet they have a library of existing symbols. So I pressed the down arrows to go down the menu, and I hit enter on library. And sure enough, I started finding this cornucopia of schematic symbols.
LS00 starting with, yeah.
Everything. It gave me a submenu that had all the
Part
different
A,
library
Part
names.
B.
It had linear.
IEEE.
Had linear, and inside linear had all these different op amps and 555 timers, and everything was in there I could possibly want. And then it had logic, and in there it had the whole 7400 series, and then it had CMOS, had all the 4000s. Then it had processors, and in there I could find this. Came with the libraries for everything from an 8031 or even an 8048 to 68,000, and I was just, my mind was blown. I'm like, I've hit the jackpot here. So you could say, so I can't stay away from ECAD. You know, I work for Autodesk now. I'm the product manager for Fusion 360 Electronics. I was a product manager for a long time at Altium, and product marketing manager as well, and at FAE. It's like I just can't stop from CAD, probably because my initial adrenaline rush and dopamine hit as a 12-year-old getting into electronics was a schematic capture program, just getting it to work the first time on an old DOS computer. And then I had a similar challenge with drivers and getting it to work with the dot matrix printer we had that came along.
And I was going to say, in the schematic for the backup alarm I did, the ultrasonic backup alarm that's still on cars today, was done on OrCAD, and I had to tape 2 dot matrix pages together to make one B-size or C-size piece of paper. And so Scotch tape right down the middle of the page.
That editing the libraries was hilarious back then. The library was a compiled binary file, and the program had these executables that would called decompose and compose.
That's right. Gosh, I'd forgotten about that.
Yeah, decompose would take the lib file and extract it into an
all the little line segments and stuff. Yeah.
And you had to open it in a text editor. And you would manually, using ASCII art, this is the cool thing, it was ASCII art. You would draw your op-amp symbol, or whatever the schematic symbol was. I think with blocks, they could be more automated, like just a pin list, and you specify the dimensions in grid units. But for other things like a transistor symbol where you put the circle and you have, you know, your emitter, base, and collector, all of that was done using asterisks across, you know, for you'd have like a
isn't
grid
that
of
amazing?
pixels, and you would do asterisks where you wanted lines to join up and things, and it was like ASCII art libraries. Crazy.
So we're being asked about your time at Altium, and somebody asked also if you knew Dave Jones from your time there, and I go so far as to say, when did you join Altium?
October 11th, 2004, but who's counting?
Yeah, that seems pretty precise. What time of day was it, Ben?
No, I don't recall. I'll tell you this, though. The reason I wanted to go to Altium and what got me the job was my interest in FPGAs, and they were shot down by the market and by the new management. For Nick Martin, the founder of the company, was a genius and very visionary. And while, yes, it's an exceptionally great schematic and PCB tool, there was a time in the market where FPGAs were the latest hot thing. Markets moved beyond that. Now, for a microcontroller, let's say, if you have you have to program something in every product. Why wouldn't you do it all in one environment? If you're an electrical engineer who does do it all, which most of us are, there's there are big companies, and those big companies have division of labor. So they have software people who don't want to touch schematics and don't care. They
Right.
just want you to tell them the pin out. Well, at least in that situation, you should be able to generate a header file that gives them the pin assignments. And I don't know why we don't have that built into ECAD tools from the schematic. You could do it in Eagle and Fusion using a ULP script. And
LPs. Yeah.
there's this one of the users who's a genius power user, Rachel Peterson from the UK. Hi, Rachel. I hope you watched this. She's actually written a bunch of scripts and shared them on the Element 14 forums to do this kind of stuff. So those things are a massive, massive accelerator and reduce and or eliminate errors.
Right. Right.
Design. So anyway, all sorts of rabbit holes today. It's not what we were going to talk about.
Oh, the chat window is very active here, people. I was going to even say, to ask what were everybody's first computers, but we're already a half hour into it and running out of time to ask that. A lot of C64s, some PCs out there. Somebody mentioned paying $5.99 for a C64. I'd forgotten that it was that price because that was before my time by a year, right? Because the price just dropped so precipitously. After $5.99, it went to $2.99 and then $1.99 real soon after that.
I don't think I could get one in working condition for that even today used.
Yeah. I have one that actually belongs to somebody, and I may give it back to him at this VCF, Jim Brain. But with that said, I want to actually bite the bullet and do a Hackaday video showing the whole family of Commodore computers from my time there. So I may ask him if I can borrow it for another month or two to do that. Oh, speaking of which, VCF is 2 weeks from now. I'll be there. I guess it's October 9th, which is a Saturday. If I had the date wrong, I mean the 9th of that weekend in the afternoon. So hopefully we'll see some of y'all there. Somebody
That's
just
VCF
mentioned
East,
Vic
right?
20. VCF East. Did I say West or did I get it?
You didn't say. Didn't specify. West has already come and gone.
VCF East. Yes. VCF West posted their video. If you Google VCF West, they've got all their videos they put online from a month ago. So there's some cool videos. Bill Mensch talking about the 6502. It's a video worth watching. So it's
Awesome.
good. Yeah. Well, speaking of 6502s, so to me, the 6502 was magic, right? That was what OrCAD was for you. I got a job at a company, so I knew the analog stuff. I shouldn't say I knew it. I learned it. I knew enough to get hired into engineering. But the 6502 was so easy to understand that it became like a religion for me. It just, I could read the opcodes without the interpreter and stuff. And what I have up here on the screen is, little did I know one day I would have my own version of the 6502, but it's mostly because we made a mistake. When we pinned it out, we stood at the photocopier and we had just gotten this thing called a 48-pin package at Commodore at MOS. And we needed to bring out all the pins that are in the Commodore 64, but I needed to bring out the pins that allowed the logic analyzer to work that would normally be unused. So they didn't make it into the 64 version. And the guys really needed this. I really needed this pin brought out. I think it was the sync pin that tells you when you're doing an opcode fetch or a memory fetch. So
Amazing
we
what
stood
you
at
can do with 8 more pins, right?
Yeah, isn't it? So
You could either go to a
unfortunately,
16-bit data or do all sorts of other cool tricks with logic.
well, and where that was headed was the Hershey bar was coming out. That's was it 60 pin? That big honking thing that the 68,000 was on. We called that the Hershey bar. But unfortunately, though, when we pinned this out standing at the photocopier, instead of making pin 1 and 48 be the corner pins, and then 2 and 47 and 3 and 4, we went 1, 2, 3, 4, 5, 6, 7, 8, 9 to 43. Well, the only way the people in the bond shop, the people that did the die bonding, which they were these elderly women sitting. They literally were sitting at microscopes in a room. I can't remember if the room had yellow light or not, but you could see it through this one glass. I remember staring in there and watching them working. They would sit there and do those bond wires manually and do that.
Not for every chip, surely.
For the ceramic chips that we needed certain runs of, yeah.
Right, just the prototypes. Yeah.
Right. Well, I'd be surprised. I think there was probably 20 women in there. So they could probably do a couple hundred a day. And back then, that was reasonable production for some chips. So some of our chips were hand bonded. I know that happened.
Wow.
So they turned the die, like you see here, and made it so that the 43 stretched up to pin 48. So this thing looked like a tie tack. It was twisted like that
for a reason. It wasn't just the way it randomly fell into the glue and sat.
So that meant that person doing the bonding actually, not only they scribed the part somewhere else probably, but they glued it down at a 45 and then bonded it out. They were so much in control of the process that we got a chip back looking like this, and it worked.
It's kind of, when I think about it, it kind of makes sense though, right? You imagine the interview process for this job. So, what do you do in your spare time? Oh, I love to knit. You're hired.
Yeah. Well, when I hired a guy named Dave Haney, which everybody should recognize from the not only the 128 and the TED, but from the Amiga, he showed up in a homemade shirt, and that told me that he could probably solder. You talk about knitting.
Use both hands. Use absolute focus and concentration, so you don't screw up.
And do it yourself. Yeah. So, and I was right. He could solder. So
you know what? Here's a challenge for the community. Wire bonding is actually, it's kind of becoming a thing in the past, but it's still required for anything with high current. It's still used in some chip packaging, but it's kind of expensive. You see that it's used a lot for multi-chip modules and chip on board. But for most semiconductors, they've gone way beyond it to chip scale or flip chip. So basically the silicon has a pinout layer that's copper, and that's soldered directly onto the substrate.
Right.
Just like a BGA on a printed circuit board. And so that's done because it's just so much cheaper and more reliable, arguably, in some ways, than wire bonding. Wire bonding is still needed for 3D chip stacks and high current. But it would be a super cool interesting project for somebody to make a homemade wire bonding machine. We do it by hand with nickel tabs for making your own custom battery packs, and that's really big stuff. I'm thinking down at this size where you use gold or aluminium wire, much like a TIG welder has, a MIG welder has the wire that comes through and melts in the weld pool in a inert gas vapor. Some mechanism like that but sized like a 3D printer, where it has a wire reel. It can start, it can go across and stop, and use some high current to begin and end the bond process.
They used to stitch it. It was how we envisioned. They had like a probe or something, and it was like a spot weld process. Is how I thought of it. I could be wrong, but that's how. Actually, here's the side of a chip. This is the TED chip, and you can actually see where this is a chip that was decapped, and you can see where the wire bonds are. You can even see it's a little off center on one of them, and there's a ghost from where the bonding wires had been.
That's cool.
So can you? Yeah, those were the days, back in my day, we hand bonded our wire. So it's boy, lots of chatter in the group today here. What do you have on the screen here today?
Oh, sorry, I was craning around to see the chat in the YouTube channel.
Yeah, somebody asked what your glove was. I answered it for you.
Oh, yeah, it's in case I use my stylus on the monitor which I'm facing. My camera's on top of this screen, so I can draw on it on a shared screen. So we might get to that. Well, for like 3 or 4 weeks now, I've been threatening to talk about bootstrapping, and we never got around to it. So I just wanted to bring up a quick example of this. So where you see bootstrapping today is mostly in power supply designs or Class D audio amplifiers. And bootstrapping just means, it's also called a charge pump. It's some way of pulling yourself up by your bootstraps is the way we call it. But it's a way of using and replenishing a charge across a capacitor, and then the capacitor jumps up to a higher voltage.
Higher potential, right.
So you think of it, I've got cups here. This is my cup, reused peach jar. But if I have 2 cups, you think of it, one cup's up high, one's down low. And while this one's down low, I can fill it with liquid, but I need the liquid up here. So I then lift up the cup and then tip the liquid up here, and I keep repeating that process. And that's a charge pump. There's a classic...
Not unlike a voltage tripler.
That's exactly what I was going to say. That's the exact same method by which a Cockcroft-Walton voltage multiplier works. Right. You apply an AC or a pulsed DC switching to a string of diodes, and you can do it with as little as 1 diode and a capacitor, basically, or effectively 2 diodes, because that's what we have with the MOSFETs here. But what we're looking at, I wonder if there's some way I could annotate this. What we're looking at here, so this is a high side FET. So this.
All right, we're waiting for Ben to come back here, but that's an enhancement mode FET he's pointing at. Go ahead.
Yeah. So this is your main switch to switch. When this switches on, the inductor is the current begins to rise in the inductor through the load and into the bulk storage capacitor here. Right?
Right.
The problem is you either have to use a P-channel FET and pull its gate low to turn it on. But the problem with P-FETs is they're expensive. They're more expensive to make, and they turn on slowly and turn off slowly. Right. So you end up with an inefficient power supply. And then you also have normally a diode pointing up here. In this case, just assume the intrinsic body diode of this FET. Normally you have a diode pointing up so that the inductor keeps the current flowing through the load and through ground, right? Which we're measuring current through those resistors, but this is effectively ground. So you have a current loop in a DC buck converter where current's flowing through the load, through ground, and returns up through this, what's normally called a freewheeling diode. A freewheeling diode automatically conducts to keep current flowing in that loop. And then you regulate it by changing the switching duty cycle. So whenever this is switched on, this voltage jumps up, this diode becomes reverse biased, the current through the inductor with the voltage pulled up at this side, the current starts to increase linearly, and then this switches off again, the current starts to drop linearly as it goes through the load, discharging into the load. And so you get some triangle or sawtooth wave ripple. And this diode normally is just a normal diode with a 0.6 to 1 volt voltage drop. So you get some loss. So what we do is we actually replace that diode with a MOSFET, and we turn it hard on during the freewheeling conduction cycle. And that through the RDS on, the channel on resistance of this MOSFET is so low that you don't get a 0.6 or 1 volt voltage drop across this while it's conducting. You get close to 0. And so it's it's extremely way more efficient. So you go from a, roughly 80% efficient power supply up to 90% just by doing that. That's called a synchronous rectifier, where you're actually using a transistor instead of a diode. And you're turning it on at the right time. And we can also, because there is a known finite resistance of the channel while it's switched on, and that's pretty closely controlled by the MOSFET manufacturer. We actually know what that resistance is, so we can measure the voltage at that point, and this shows us the exact current through that chip. So we can actually accurately measure the on current through that and do some current limiting or measurement as part of the feedback in our controller. So that's all cool, but we still have this problem that an enhancement mode MOSFET turns on when the gate voltage rises above the source voltage, which is this midpoint here. This midpoint here, we want to turn that on, and it has to go up to the input power supply voltage. So we effectively want this MOSFET to turn hard on. Well, at first, we can't turn it hard on because we don't have 58 volts driving the gate. The gate goes into the chip here, and that's got a gate drive circuit that's powered through. This is a linear regulator that gives us, I don't know, probably 12 volts, right? I don't know what the value of that Zener is, but this is a simple linear regulator, gives us a 12-volt output, say, and so we can't turn this MOSFET on easily. We could basically get some leakage through it, but we need the gate to turn it hard on. We need the gate to. Oh, I can annotate things. Where is that? Where's that tool in Adobe? I want the highlighting tool. Why can't I do it? Maybe it only works with text. Yeah, maybe it only works with text. Oh well, I'll figure that out for next time. So we want that gate voltage to be able to rise above the input power supply, which could be up to 58 volts here.
Right.
So here's the trick. We know this node here is getting pulled down to 0, and then it's getting released, and when this is turning on, it's getting pulled up to the power supply. So we tie a capacitor to that, and we have another input to that to measure the voltage there in the chip. We tie a capacitor to that. When first powered on, that capacitor is charged through D1, and this is pulled low by Q3. So this capacitor charges up at least to 12 volts. And then when Q3 turns off, this floats up and because this capacitor is charged, this voltage on the top of the capacitor rises up to whatever. This floats to 12 volts. We can control this inside the chip with this VS pin. We can pull this up at least to 12. Then this capacitor has risen to 24 up here. And the chip does that a few times on startup to the point where this VB voltage is now rising up above our input voltage here. And that's powering the gate drive amplifier, which is probably just a kind of op-amp inside this chip. That's then allowed to drive the gate to whatever VS is, plus the 12 volts needed to get this transistor to turn on hard. So the whole thing gets bootstrapped using this charge pump scheme. And that's bootstrapping. Now that's where you typically see it in, it's almost always in a power supply or, as I mentioned, Class D audio amplifier. On startup, the chip goes through a few cycles to pump, and get that capacitor voltage up so that so you can drive something harder. But interestingly, bootstrapping was originally used in analog circuits.
Right. And that's where I knew it from.
I've seen it used in bias servos in Class A, B, and Class B audio amplifier output stages, a power amplifier. And I have another example of its use in what's called a mu follower, which is a really interesting circuit. This circuit was originally actually done using triodes. So you'd have two triode valves or tubes, electric tubes. So this is old technology, but it works so beautifully. So what I have here is effectively a common source amplifier, and you get with a JFET, you get nice high input impedance. This is my input here. You get a nice high input impedance, and you get pretty high gain. But the gain, it could be wildly varied because JFETs, just the way that they're manufactured, there's a lot of variations in their characteristics, even within the same.
Right. You're breaking up a little.
Numbers. We control the gain.
And you're back.
We control the gain by, yeah. Okay, so I was saying we control the gain by adding a source resistance that provides a bit of negative feedback. So we lose some gain, but the gain's more predictable. And normally on the drain, we'd have just a load resistor, and then we have our inverted output. But the gain is going to be very limited because the output impedance of this circuit is also pretty high. And so unless it's also driving another JFET stage that has a very high input impedance, the output loading on this gives us a fair amount of loading will reduce the gain as well. So how can we get more gain? We can add another JFET as a kind of current source. So that's a variable load. This is still a Class A amplifier. Q1 is doing all the amplification. Q2 is just a load, which is biased and acting like a variable resistor so that it allows a little more gain. It will distort a little bit too. It gives more distortion, right? So, but what I want to do now is add a component to this. Where's my library window? I guess it's synchronizing something with the web here.
Yeah, we see the little spinning wheel there. Yep.
Come on, Fusion. Where are you? Oh, where did my library window go? I opened it and lost it right away. Or it's on another monitor somewhere. Let me find it. Oh, here it is. Here it is. Somehow I let it go behind. So I need to, let me find my own library here. Tons of parts in here. So if I go here, I want to find a small 10 microfarad capacitor. So this is where the bootstrapping comes in, right? Tantalums are not bad for audio applications, so I'll go with a 16-volt tantalum.
I always thought of them as relatively low noise.
Yeah, I've seen them used a lot in analog audio because of that, especially in power supply decoupling.
Right.
And that's because, I don't know why. It's just the way they're made. It's like tantalum forms this sort of spongy metal that has a massive surface area. That's a whole other, it's a whole other stream we should do one of these days. Yeah, how different types of capacitors are made, because there's a lot of interesting stuff to unpack there too.
Or what I even mean when I say low noise, and I'm almost quoting that, by that I mean it inserts a low Brownian component of its own. It's smaller compared to others that generate random noise themselves as components.
It's also like, if you think about an electrolytic capacitor, it's very thin film deposited. It's either very thin aluminium foils with a electrolyte soaked paper between it, and it's all rolled up into a coil. So there's some natural increased series resistance and inductance, both because the aluminium's not a great conductor and there's a lot of it across the whole plates of the capacitor. Right. And because of the way they're coiled up to be round and small, there's going to be a significant increase in equivalent series inductance. Tantalum caps, on the other hand, have microscopic, it's like activated carbon almost, only it's not carbon, it's tantalum, metal. And it's so this small compact block of what's like foam made of tantalum, and so it has
Okay.
massive surface area.
Right.
And then
Right.
they attach that to one electrode and put another electrode, and then the whole thing's got electrolyte in it, similar to an electrolytic, and it's sort of, I forget the name of the process there. They apply a voltage to it to bias it to, and this is why capacitors are polarized as well.
Right.
And that forms an oxide barrier around all of the tantalum surfaces, and
Now,
it's
hey,
pretty incredible.
do you remember seeing non-polarized aluminum electrolytics? We used to see
Yes,
them in crossovers of speakers,
yes, and you can
4 microfarad. Yeah.
still get them. Well, and also a variant of that is still the polyester film capacitors,
Right. Right. Right.
and but non-polar electrolytics, what that really is it's instead of two plates with a single electrolyte paper between them, it's two plates with a plate in the middle and two sets of electrolytes, and
Okay.
they're biased both ways in the factory during totally brain farting on the word they use, where they initially apply voltage to it
Like phosphoretic or
they
something
set
like
it,
that.
but
Yeah.
it's equivalent of two polarized capacitors back to back with their positive electrodes on the outside. And you can make your own non-polar electrolytic by joining
With two diodes.
two polarized electrolytics with their negative terminals together in the middle. You get half the capacitance and double the volume. So it's
I remember seeing a version of that, but yet still protected with diodes, since you couldn't count on them to balance 100%. You could
right.
put a protection diode in there so that each cap only saw its specific polarity.
Yeah.
I don't know what that did for audio noise, but yeah.
It would probably add distortion, but yeah.
Yeah.
It'd probably generate some kind of crossover distortion as the diodes. But if you're dealing with super high voltages, it wouldn't be enough to notice. So what I've done, I've added this cap with the negative terminal at the drain of the amplifying transistor, and the positive terminal at the gate of the active load. And what that does is when my input signal swings low and this Q1 starts to turn off, the voltage on the drain of Q1 rises because it's an inverting amplifier. That rising voltage there, this C6 is at steady state, charged up, and appears like a short circuit. So, but with a DC voltage across that of close to our power supply voltage, or what would it be? It would be power supply has got this 50-50 voltage divider here, so it'll be half the power supply voltage. So what happens is, as this transistor begins to turn off and the output voltage rises, it pushes the gate voltage up. The source to gate voltage rises with it, and so Q2 begins to actively turn on and conduct, and that adds more current and pulls the voltage higher yet. So this now starts to add gain and reduce output impedance of the whole amplifier. And so instead of getting a gain of, say, 50 or 60 with this circuit, I can now get a gain of, say, up to 150. So this is a very classic circuit. It's used in some guitar amplifiers. This here is like a booster pedal that will drive the input stage of a tube amp into really nice overdrive and make a beautiful crunchy sound. So so this is another form of bootstrapping in this, what's called the mu follower. It's called mu follower because in old times with valves, the gain of the valve, and in some data sheets even with JFETs, because they behave very similar to valves, that the term used for gain, or for intrinsic gain, is mu, the Greek letter.
Okay. Yeah. MU.
So, yeah.
which you know, the other usage from you I've heard is for metal that's capable of shielding magnetics. We call them U metal. I guess it's got a little bit of
That'd be a
cobalt
cool
in
name
it or
for a
something.
band or a style of music.
Cobalt.
Yeah.
So, very cool. Very cool.
So we finally got around to talking about bootstrapping in two different
In audio, yes.
bootstrapping in audio and the I was going to mention the other one that I've seen. I'll just draw it real quick. Is that if you have a Class B output stage, so I have this kind of circuit, right, driving the output of a power amplifier. There's VCC, VEE, which is negative power, right? And there's our output. And to bias these transistors so that they're just at the point of starting to conduct at quiescence, you'd have to overcome the VBE, the common PN junction forward drop, which is usually 0.65 to a volt, depending on how the transistor is being used. So the old school way of doing that is you just put a couple of diodes, right? And you do this kind of thing. Output current to drive the power transistors of your output stage, and so this works, but you still get a bit of crossover distortion, and it's non-perfect because these forward these PN junctions are not, the diodes aren't exactly matched to the transistors and so on. So the other way this is done is this whole circuit is replaced with what's called a bias servo, which is, it's one of these jobbies. You're using a transistor for its forward drops, and you have a potentiometer, and you swizzle that with a screwdriver while measuring your quiescent current with an ammeter, right?
All right.
And you set this to be whatever you want it to be. So maybe if this was a 100 watt amp, you might set that to be 0.1 amp quiescent current. So it warms everything up and then stabilizes, and you get low distortion that way because both transistors are slightly conducting. And so that's cool. That works. Well, what I saw, and this came from Horowitz and Hill's book, you know, the famous book, The Art of Electronics. They said they had this whole paragraph on bootstrapping this thing. So you put a capacitor across that to reduce distortion even further, because this whole circuit is being a servo, and with intrinsic, you know, or parasitic elements around it, capacitances and things, when the voltage down here rises, yes, it's all based on current, but the way this thing reacts to that rise in voltage may not have a matching current exactly, and so you get more distortion. By adding a capacitor across here to AC, to the actual audio signal, we've effectively taken this whole thing out. So this is only then effective for the DC biasing requirements, and your audio signal that's turning the top and bottom transistors on and off, or, you know, driving the output transistors, is effectively short circuit to AC. So that's just the other place that you'll see bootstrapping.
Okay. All right. Yeah, somebody mentioned you could, to do your little twiddle adjustment there, you could throw a signal into it and watch for crossover distortion.
Yes. You have to have a good oscilloscope with really good dynamic range and to zoom right into the crossover portions of your waveform.
Right.
Or if
So-
you've got the money, you buy a HP. I forget the part number. It's 80. It's not 839. It's a 4-digit number, but an audio analyzer that has a really ultra low distortion precision output and a distortion measurement input, and it can sweep the whole frequency range. Or if you really have the money, like tens of thousands of dollars, you get an audio precision. They're like the industry test set standard.
So how do you measure total harmonic distortion? Do you compare the output you get compared to a super standard, or what's the best way to measure distortion?
Well, distortion.
What's that equipment do that you just described?
Yeah, first think about what distortion is. Distortion is something
It's not supposed to be there.
that's not supposed to be there according to the input. And an audio amplifier is just a device that ideally is pure gain and nothing else. So the output must exactly be identical to the input, only higher power or higher voltage. And so what an audio analyzer does is it has a extremely you have to start with a very high quality clean signal source. The signal source itself is not perfectly sinusoidal. It has some harmonics and some distortion, but you get it as good as you can, and then there's some residual crap in that, right? So you take that and you measure your signal that's going in, and you measure the signal that's coming out, divided by the gain that the whole amplifier is supposed to have.
Right.
And then you subtract
One from the other.
You subtract one from the other, and what's left over is distortion, is THD.
Right.
And
right.
And then you display that on a graph or whatever. But there's
Very good.
a number of schemes to do it. Anyway, we're
cool.
past the hour. How did that go already?
Yeah, because we were having fun. So it's, hey, I did bring up, we were talking about CRC generation, so I grabbed this off the web to help visualize when I was talking about a bucket brigade with some exclusive OR going on. I never really did the math for CRC, but this is a typical CRC generator, and this is what the dongle and the ORC had when we looked at it. This is the circuit it used.
Yep.
And you can do various taps of the exclusive OR to create various polynomials.
Yeah, the wiki article on this is pretty cool. Someone actually went to the trouble of building this with LEDs on a breadboard to show the pseudo-random sequence generation.
That sounds interesting. I actually stopped pausing there for a second and going, well, I could build one of those if I had the time and inclination. Yeah, that'd be kind of cool. So what was this? What was COCOM? Oh, somebody's asking somebody else what COCOM was. I don't know what that word is. So, all right. Well, hey, it was good speaking with you again. Great class here on bootstrapping and some of its uses.
Yeah. Well, let's hope we find the time to annotate these on YouTube, and then people can start to discover what we're talking about here.
Yeah.
And to all of you who are watching live, thank you for joining us, and we really appreciate it.
Yeah. We posted the Discord channel invite at the beginning of the chat, if you care to keep the conversation going, as they say.
Yep. Sometimes it's quiet, sometimes we get quite lively.
Yeah. Well, and that's a problem. We get so much going that it's hard to find the end of the conversation and work backwards. You know, so we need to figure out a good threaded way to hold multiple conversations at once.
Right.
So
right.
Well, yep. Ben, my friend, it was great seeing you again. We got to figure out what to talk about next week. If people want to post that to Discord, we'd love to hear about it. What would you like us to talk about?
Definitely. Get on there, go into the topics-feedback channel. Tell us what you want us to go on about, and or if you have any Any questions?
Or-
Also, bear in mind, Bill's like massively experienced hardware engineer. Me less so, but I've spent my whole career basically in the printed circuit board sort of space.
Right.
So really,
Right.
between us, there's probably some areas we don't know, but we can have a crack at anything.
What we don't know, we can make up, I always say.
Yeah, exactly.
So, yeah.
Or invite you as a guest to join us.
Yeah, if anybody'd like to join us, that's a great comment. Johan Grip joined us. Maybe we could get him to, if he can do Skype, we could talk about the process of creating this creature, which is recreating it, I should say, the C128 board based on a 40-year-old board.
That is incredible. That's a labor of love, and it's incredible. And I have so many
Oh, we lost you.
questions.
Okay, we lost you. You're back.
I guess I came back right at the end
So-
this time.
Yep. All right, so we will see everybody here next week. Ben, my friend, we will see you also here next week.